Started. Let me introduce Dr. Ananda Mohan. Uh, he received BSc and MSc Tech degrees from Andhra University in 1965 and 1968 respectively, and the PhD degree in Electrical Communication Engineering from Indian Institute of Science, Bangalore in 1975. He was with ITI Limited R&D from 1973 till 2003, and later was with Electronics Corporation of India Limited, Bangalore, in their R&D division. And he was there till 2016. He was later a technology advisor for CDAC, Bangalore. His research interests are in the areas of mixed signal VLSI design, VLSI architecture, and cryptography implementations. He has published in these areas in reputed international journals and conferences. He has co-authored 5 books. Those books are Switched Capacitor Filters, Theory, Analysis and Design, and co-authored with Dr. M.N.S. Swamy and Dr. V. Ramachandran. And it was published by Prentice Hall in 1995. And 4 more books, Residue Number Systems, Algorithms, Architectures, which was published by Kluwer Academic in 2002. Another book, Current Mode VLSI Analog Filters, Design and Applications, Birkhauser in 2003, VLSI Analog Filters, Birkhauser 2012, and Residue Number Systems Applications, Birkhauser 2000. Dr. Mohan is fellow of IEEE USA, IEEE India, National Academy of Engineering, FNAE. He was the chair of IEEE CAS chapter, Bangalore, since its inception in 2008 till 2018. From the beginning till 2018, he was the chair of this our own society, CAS society. He was the associate editor of IEEE Transactions on Circuits and Systems and regular papers during 2000 to 2003. He is present an associate editor of IET Journal of Education and Circuits and Systems and Signal Processing, CSSP, and it is by Birkhauser again. He was with Center of Advanced Computing, CDAC, Bangalore, as technology advisor since 2014. So after this brief introduction, I will invite Dr. Anand Mohan to take over the stage. Sir, over to you.
Oh, sir. Thank you. So it is very nice of CA's chapter to invite me for giving this lecture. So I will take maybe about 1 hour. I believe will be of all circuit systems members as well as solid state circuits also, because today in all integrated circuits there is nothing without a filter. Okay, so
decrease the chance.
yes. So now this agenda is this brief introduction for the area. Then I'll briefly tell about what are general filter design considerations. Then what are the various technology options and various structures that are available, and then make some concluding remarks. Now, if you see today, if any DSP based system, like your mobile phone, for example, is a DSP based system. So what we have got is we have microphone and earpiece, but after that we have got analog interface. That means something like amplification, something has to be done. Then there will be something like band limiting filter, because you have to, whenever you try to sample some signal, you have to follow certain rules, like you have to band limit the signal. So one band limited filter will be there. After that, A to D conversion will be there. Then thereafter, digital signal processing can be used for storing or for crunching this. That is like all your low bit rate coders, everything need DSP. So all functions will be done by the this DSP digitally. Similarly, on the receive side, the DSP will receive the bits from foreign, then you have to again convert it back to analog. So similar chain is there, like D to A conversion, and then there will be a smoothing filter, because D to A conversion output will be a sort of staircase type of waveform, because the speech would have been sampled at 8 kilohertz and given. So during that 125 microsecond period, it will be constant. So now what do you do to get a smooth signal from there, that which looks like normal signal, which is not sampled and held, you have to use a smoothing filter. So that means this you take any system like video codec or whatever system, or Wi-Fi or Bluetooth, everywhere, whenever you have got analog signal to be converted to digital form, you must band limit. So filters are unavoidable. So actually the whole technology of filters has been driven by the industry's need for these filters. Now, when it actually started, when Opamp was invented, before that people used to use vacuum tubes. In fact, some of the key papers in this active filter area were published, by Salon and Key in 1955 using vacuum tubes. So afterwards, Opamp has come. So active RC means some active element should be there. So Opamp should be used. Then afterwards, because once MOS technology came, they thought that some limitations of this, which we are going to see, active arc can be eliminated if we have a switch capacitor technique. Then what people thought was switch capacitor again will have some disadvantages, like need for clock frequency, something like that. So what they have done, they went to again back to something known as continuous time. Active RC is also continuous time only, whereas switch capacitor, it is like a sampled data system. So now again they went back to something which uses instead of op-amp operational transconductance amplifier. In the olden days, we used to that is op-amp has been designed to drive a low load, whereas here, in MOS, we don't need to drive a resistive load much. We need to drive only capacitive load, that too because of various constraints. Maybe maximum people want in a chip is maybe 100 PF or something. So that means there is a overkill if you want to use op-amp. So people have gone for something known as OTAC, and similarly, this is another version is GMC. Then people thought, why don't we work in current mode itself when instead of voltage mode? The reason is power supply voltage has come down now. People say earlier we used to have, if 741 is plus 12 minus 12, I used to use in my childhood. But today people say want to work with 1 volt. But signal dynamic range has not changed. Our speech level is same. Our whatever signals we see, they are the same level. So that means I should have good dynamic range, but power supply voltage is less. So people went to current mode. Why can't you work in the current mode? So like this, what happened is based on the technological developments and needs, by technology, this it has evolved. Then people have some thought, instead of resistors, why don't you use a MOS transistor as a resistor? In fact, this is a very old idea, but again they have resurrected. Then most recent ones are ring oscillator based. That means this they thought ring oscillator is easy to do because you have to put a chain of inverters in a loop. So that's why an inverter just needs two transistors. So why can't we design filters using some of these concepts? And more recent one, a millimeter wave. You must be seeing, when we are going to 5G and above, up to we may have to work at around 80 gigahertz. So then people are trying to use something like this all waveguides and all. When that they are made being made on the chip itself, like planar waveguides and small lambda by 4 line transmission lines, but they use some negative resistances also. So that millimeter wave now it is actually a developing area where a lot of filters are being developed. So that means lot of design choices are there. So that means if you are given a task, design a filter for a particular application, you have to weigh lot of aspects, like area, power consumption, and need for some other support like clocks and all that. So based on that, you have to take a decision. Now briefly we go through each one of these. This already I have mentioned. Power consumption, supply voltage has to be low. Then some case clock is required, and dynamic range has to be good. Dynamic range in fact has become important because today mixed signal means both analog and digital are on the same chip. So that's why what happens on the power supply pin, there will be some clock noise will be there. So on the one side we are having clock noise, and there may be something like ground noise may be there. So dynamic power supply voltage has come down. So that means this your range for your operation, actual signal has become reduced. So we should still be able to handle that. Similarly, frequency of operation also. Olden days, only voice frequency. When actually filter design started, people were telephony was the major application. That means voice band filters. Whole technology developed. Intel has made the first PCM filter. For Intel imagine microprocessor company, but they have made for a voice codec. They call it as cofidec. That means codec plus filter. So frequency optimization today people want to work at very high frequencies. That is, there is nothing like low frequency at all. Low frequency also difficult to make. For example, biomedical signals, they may have to do filtering for say 10 hertz or less than 10 hertz. So what happens? The capacity values and all become big. So how to this realize? Even in such situations. So continuously people are working. So we are worried about total area, total capacitance. I told you 100 PF or something like that. And big resistances, there are many techniques of realizing, but we don't want to use like our old, this resistor. Resistor value is proportional to length. So you can't say I will have a big polysilicon strip, to cause resistance. So some tricks you have to use to realize high resistance. Okay. So and Opamps of course don't occupy much area. Okay. Then sensitivity, because today once you make a chip, any design you do, first reviewer will ask you if you submit a paper. Have you made PVT variation study? Okay, because that these are all important for practical applications. Okay, so some room temperature it may work, but under certain conditions, it may not work. So for all the worst case limits, you should see what is the this sensitivity of the circuit. So there are some theoretical measures, but first theoretical measures we should have. Then you can say simulation will support Monte Carlo simulation and all, whether your conjectures are good or not. Then sometimes tuning will be required because you see all said and done. There is nothing like ideal resistor or ideal capacitor in a MOS circuit, because everything is having because everything is depending on the mask only. So mask as well as for example capacitance is defined by not only mask, like oxide. What is the dielectric constant of the oxide? So that means nobody can similarly polysilicon resistor value may vary from maybe 10 to 30%. So how do we take care of that? So that's why what we need something like tuning. Olden days we used to have potentiometers and all, but today you can't have no external control is allowed. That means there should be some automatic tuning mechanism inside. So outstanding work has been done in most of the chips where just nothing is required to be done outside by the user. That means you just fabricate the chip and it will automatically adjust itself to the required specification. Then good power supply rejection. This is also because these power analog signals are there and you have digital signals on the same chip. So that clock noise you should be able to not pass to the output of the analog node. Okay. Similarly, spread also. For example, in digital filters, you can have a spread of even 16 bits, because digital filter they say coefficient can be 16 bit because there is nothing there. multiplier you should have 16 by 16 multiplier, or something like that. But here, unfortunately, the maximum capacitor value you can get in VLSI, is around 1024. That means compared to the smallest one. That smallest one we call as unit capacitance. Unit capacitance means, suppose a 180 nanometer process, 180 nanometer by 180 nanometer square, whatever capacitance it gives, that is known as unit capacitance. Now, with reference to that, maximum 1024 times you can get. That means the dynamic range of 10 bits you can get. That is the difference between this DSP and this. But still, we should be able to manage this one. Then ease of design. In fact, what happens, technology has been developed to say we don't need analog experts, because analog experts are very expensive and very few. So what they say, make analog very small as possible, and only everything let it be digital. So this is how, for example, sigma delta modulator has come. Because this oversample AD converter, the beauty is just you need very little analog circuitry. Hardly you need one op-amp, one comparator, and one D flip-flop, and a few capacitors. Okay, so that's what these are all the things designers expect, and programmability should be there. There are many commercial chips available where some applications like automotive and all. They say we should change parameters of the filters, like I want to change the Q, I want to change gain, I want to change center frequency. So all these things you have to do. So these are general design requirements. And then once you have decided on something, you have to know something like specification is given. Now once specification is given, there are many tools available, like even MATLAB you can use, where these filter design packages are there. So it will tell you what is the transfer function. Transfer function in terms of say this HS, numerator by denominator, and numerator is having this something on zeros, and denominator having poles. Now once you get the transfer function, you can, because suppose it is a 10th order transfer function, you can realize it by means of a variety of means. For example, this one is a cascade design we call. Cascade design means, I suppose 10th order filter means 5 such stages I use, and each stage is having that HS I have given below, second order transfer function. Okay, so that means this once you synthesize transfer function using some tool, okay, then you can arrive at the values of these parameters, like omega z is called zero frequency, omega b is called pole frequency. Similarly, qz is this zero q, and qp is pole q, and k is the gain. Similarly, if it is suppose odd order filter, say 7th order, you need 3 such sections and 1 first order section, which is that left I have shown 1 by 1 plus SCR. So that means now why they went for this design is you can standardize on a good second order filter. That means second order filter which is having, in fact in general, numerator 3 coefficients are there, denominator 2 coefficients are there, gain is there. So that means if I have a general structure, then I can realize anything I want using this. So that is what I want a biquad. So considerable work has been done in the past 50 years on designing biquads using various technologies. Now this I just skip, so this is first order low pass filter. So transfer function you got from synthesis tool. Now if you want to implement, you have to use this structure, like from denominator 1 plus SCR, you have to identify SCR, and you can use any product of R and C. Here you can see what is convenient for you. If C value you want it to be less, or C value to be more. So based on that you can choose. Similarly, this is a high pass filter. So this these are all first order sections. Similarly, there is something known as this all pass filter. All pass filter means it for all frequencies amplitude is 1. You can see 1 minus SCR by 1 plus SCR. This is purpose of this is something known as a equalizer, because it gives you delay. That means if you write for SJ omega, you will find this, you can derive the expression for phase. Derivative of phase is delay. So that means this gives you delay. Delay is required in many of the applications. For example, this radar, today you have got some beam forming. Beam form, I want to get different signals with different phases. So for that, to be achieved, you can use some phase shifter like this, so which doesn't mess up with the amplitude. It only changes the phase. Now, if you want an active RC version, this one of these two side, using Opamp you can do, because what happens here, the top one cannot drive a load, because suppose I connect a resistance at the output terminal to ground, that affects the transfer function. It will no longer be 1 minus SCR by 1 plus SCR. So that means, if somebody says, I don't want this to be loaded by next block, we have to use the other two. Okay, any of these two you can have. Now, in technology, again, suppose I give you these two circuits, which one you prefer? Is this top one. You know why? People say we have to use grounded capacitors. The reason is, if you fabricate a capacitor in a MOS chip, what happens is there will be a some sort of bottom plate. That bottom plate is actually having a diode to the substrate. So that means, because it's a polysilicon, and top there is a metal. In between dielectric is there. So that bottom plate parasitic capacitance is, value will be around 30% of the actual capacitance. That is, if you fabricated a C of 50 pf, that parasitic capacitance may be 15 pf. So that you don't want it to affect your circuit, because in this left circuit, it may happen. That's why what you do, you have to be careful in connecting where to top plate, where to bottom plate. For example, in this lower circuit, we have to connect the bottom plate to the source, so that the parasitic will not be having any effect. Okay. So similarly here, that is why this you have to connect always bottom plate here to ground in the top circuit, and top plate only is having parasitic because of wiring. So that is generally, you can control by proper routing and all. So these are all the considerations, we have to see before actually embarking on a design. Now latest one, this, I am telling you, this all pass delay for beam forming only. Now, actually this circuit was, designed using vacuum tubes in 1950s. That means in those days they used to do, because this they used to call paraphase amplifier. Paraphase amplifier means, I get Vi at the bottom source terminal minus Vi as the drain. So I am driving this. That's what earlier previous slide I have shown you. Vi and minus Vi. So how beautifully you can do Vi and minus. Of course, source impedance, you see, top one impedance is having Ra, and this resistance of the FPT, that is RO or something. Whereas bottom one is having relatively low, because it is a source follower, this output resistance. Okay. So that means, if you have to analyze all this, you have to simply drawing, that like previous one, schematic is simple. Where from you get minus Vi and Vi. So that's why, you have to analyze all. So these are all recent circuits, and to this today people are using left and right this in some of these beam circuits. Similarly, differentiator is there. So because this all these basic pulse starter building blocks, we need. Now, if you have read some books, people have they written like this: differentiator should not be used. You know why? They say because high frequencies, it that is high frequencies it emphasizes. So noise will be emphasized. High frequency noise. Actually, this is a rotten idea, because that olden days, in 1950s that was true. But today, whatever you do, you should not just go with that idea. You should analyze and then come to a conclusion. When you analyze, you find that, which we will see later. This is as good as a this integrator. Differentiator and integrator both are having the same properties. That is, nothing will amplify noise more than the other circuit. Okay. So now, if you want a lossy integrator, this right bottom circuit you have to use. Similarly, this is lossy differentiator. Now, how you introduce loss is, capacitor is a energy storing element. So suppose I remove the energy, it becomes loss. I introduce loss. That is how, that is what we also call damping. What is damping? R2 is called damping resistor. That means, whenever energy storing element is there, if you shunt it with something, obviously, that capacitor has to discharge through that. So that's why, so this is known as lossy differentiator and lossy integrator. Then this negative resistance, I was telling you in millimeter wave circuits today, people want negative resistance. Okay, in actual microwaves, there used to be a lot of negative resistance devices like impact diode and trapad diode and all that. But now, if you want, now people are using actually negative resistance circuits. These are all very old, and people thought, they are not that useful. For example, see here, how do you get negative resistance? This, we are having input. Now, suppose this this one is easy to explain. Right side one, input is amplified by twice at the output of the op-amp. Now, what is the current through this resistance R1 is Vi minus 2Vi by R1. That means minus Vi by R1 or Vi by minus R. That means it looks as though there is a negative resistance in that. So, see how beautiful this circuit is. So, this today again people are using to solve some problems. I will just tell you later. So, actually this was the one circuit designed by this Debu, one very famous circuit, Debu integrator. You can see, suppose somebody says, I want non-inverting integrator. What we will do, we will say, this you have bottom circuit, you see invert signal, then inverting integrator. Inversion plus inversion will make it non-inverting, and this is the integrator, non-inverting integrator. But again, here, can we reduce number of op-amps? Because these are all the issues even today we are having. I want to reduce power consumption. So I don't want to use two op-amps. I want to use somehow one op-amp at the expense of something. So here you see beautifully this Debu, what he told is this you put a negative resistance across C, and then RC and this, if you see this derived transfer function, you will find that this is a beautiful non-inverting integrator at the input of the this in non-inverting input of the op-amp. Okay, but price paid is you need a buffer. If you can't directly load this, you need a buffer. Okay, so these are all some of the old ideas. Now today people also go for differential circuits, because when you have all this differential signal, common mode signals, like I told you power supply noise may be there, or some ground noise, something may be there. So all this we have can be reduced if you use this fully differential circuits. So this now that's why invariably they may show you single unit circuit, but they will write somewhere that is fully differential implementation has been done. Okay, so that means what is the price you pay is you should have mirror image of the this top circuit, whatever is there with the of the mirror image in the bottom. Okay, but there is another problem. How do you ensure minus V0 is exactly this same as modulus is same as V0? So that's why what they do, differential output op-amps have a lot of internal requirements. That means they have something known as this one balancing circuit. That means it senses V0 positive and V0 negative difference. Then it adjusts there is a feedback loop which adjusts the gain such a way both are becoming equal. So that is how today invariably, fully differential I may show, but there will be one this balancing circuit. Okay. So these are all things. Now this is actually, this is how normally people, beginning used to do. That means I have just some amplifier, output I am putting inverter. But again I told you this is what we call as unbalanced. That means out plus is not equal to out minus. Okay, so that's why unless you use that some loop, control loop, you will not be able to achieve that. And these are all very old ideas. I will not bother about. These are full cascade circuit, and see for example that 40 case, 240 case, and this 1 PF resistors. What it does? It takes plus V0 out plus out minus. It adds. Beautifully what happens if they are equal, you will get 0 there. No voltage will be there. Because Vi plus minus Vi are adding. It is superposition you have to use, theorem you have to use, then you get 0. But if there is difference, the transistor M6C will get some signal, and that will this loop, so that it somehow it makes those two outputs, equal. Okay, these are all available in books, you can refer this, maybe Allen and Hallberg or something like that. Now we are telling second order filters, this I have already mentioned, this is general one. That means numerator will have 3 coefficients, denominator will have 2 coefficients, because D2 you can divide by, and that is a gain version. Now, many types of transfer functions are possible. That means, once you use this filter synthesis tool like Filsin or MATLAB or something, you will get something. The one maybe this is one low pass. Low pass also can have a peaking depending on the value of Q. Similarly, this bottom second one is high pass. Third one is a band pass, and this is a notch. Okay, in fact, suppose most of our systems, we need 50 Hz I want to reject because power supply hum is everywhere. I need to put a notch filter. Especially biomedical systems, they have this notch filter. So, this next one is known as low pass notch. That means it is the low pass filter like thing only, but it has a notch frequency at frequency greater than the peak frequency, pole frequency. Similarly, the bottom one is known as high pass notch. So these are all the various transfer functions. Now, in fact, this Allen and Key filter I was telling you was described using vacuum tubes in those days. Most famous even today, most of the systems front end is this. And they design it to be a this second order Butterworth filter. You know how simple it is. R1 is equal to R2. C2, C1 is equal to 2C. That means 2C, how you realize 2C? You have to put two capacitors in parallel. Suppose C2 is 1 unit capacitor. C1 is 2 unit capacitors. That is two unit capacitors you fabricate and put them in parallel. Okay, that process. So now the beauty of this is, for any filter, this pole frequency is dependent on 1 by root over R1, R2, C1, C2. So obviously, here what we have done is C1, C2 ratio we have maintained, R1, R2 ratio is 1. So if you actually derive transfer function, you will find that this pole frequency is sensitive to all the 4 components. So suppose each component varying by 1%, that C1, C2, R1, R2, it will happen that omega naught varies by minus 1%. Because 4% minus 2%, because 1%, that is total 4% variation, bottom, square root, so 2%. And because denominator it is minus 2%, that means as capacity value increases, frequency decreases. So that means 2% variation will be there in omega naught, whatever you do. So only in circuits where such tolerance is acceptable, you have to use this. If you say, no, I want exactly 30 kilohertz, my pole frequency, you can't use this, because unless you use some trimming. But trimming is a laborious process, So, but here, what you can see, Q can be made as only ratio of capacity. I was telling suppose K is 1, that is amplifier of gain, that is just a buffer if I have used. When you analyze, you will find that this Q is nothing but, suppose I want a Butterworth filter, the ratio of capacitor is 2. That's why I told you one is 2Cu and another is 2Cu. Okay. Now, you should worry about, it is not enough just to do this. You have to analyze what is sensitivity. Sensitivity means, suppose I want to change a component by 1%, how much change is there in the this pole frequency omega naught and pole Q. Pole frequency I already told you. Worst case, 2% it can be there. And many of these components, some may have positive tolerance, some may have negative tolerance. Because we fabricate, we don't know, plus or minus something may be there. So that's why what we do, Monte Carlo simulation we do. That means I will vary all the components in a random walk fashion. And worst case frequency response I will plot. And that ensemble of all those curves, I will see whether it is within my limits. Because you always should specify, this is my margin. That means I don't allow my transfer function to fall outside this range, my gain to fall outside this range. So you have to verify that. So for that Monte Carlo simulation we do. Okay, so these are all some of the things. So generally what we do, you should not go to simulation straight away. If a design is good on paper, then only you should try to simulate. That's why we derive all these suppose you use the amplifier of gain K here in the previous one, okay, generally, then what happens is sensitivity you see is proportional to 3Q. That means if your Q is 10, your component, gain varies by 1%, your Q varies by 29%. That means it is a useless circuit. That's why what you do, don't try to use this circuit. For high Q, don't use this circuit. Q of 10 and all you should not use. That's why industry what we do, whenever Butterworth filter you need, you can use. Because Butterworth filter Q is 1 by root 2. Substitute here 3 by root 2 minus 1. That is fine. 2 point root 1 by root 2 is 0.707. So 2.1 minus 1 is 1.1. So that means you have to use this circuit in situations where tolerance you can accept. Now next point, today we are worried about this non-ideal op-amp, because in childhood also we used to teach bandwidth of op-amp is 1 megahertz, 741 1 megahertz. But we never bothered about what is there a side effect of that. But actually today it has become a big problem, because once you want to design filters for high frequencies, okay, then this op-amp bandwidth has to be modeled. So that's why there is a model like this. This is what is known as single pole model. That means it is op-amp is like an integrator. Gain falls off with frequency. Any system, in fact, in the world, any device, gain has to fall with frequency. So it takes differential input VB minus VA, and B by S plus omega A is the transfer function. So B is the unity gain bandwidth, and omega is known as first pole. Suppose 741 you take, B is 1 megahertz, omega is 10 hertz, because B is A0 into omega A. DC gain of op-amp is, the bipolar op-amp is 100,000. So 100,000 into 10 hertz is 1 megahertz. So that is how. But today MOS, unfortunately, this you can't get 100,000 gain. You can get maximum 10,000 great difficulty you can get. And omega A of 10 hertz you won't get. Because bandwidth here we are getting more, 10 megahertz. But this division between B and omega A is different today. That means omega is maybe 15 kilohertz or something, and this bandwidth may be 10 megahertz. Okay, so that's why what you do, this you have to analyze the effect of this bandwidth on the designed circuit. So that means now I will give you a simple question. Suppose I ask you, I have given you two circuits, one with gain 1, that is buffer. Another also same thing with gain of 1, but it is gain minus 1, because this is inverting amplifier. Now, what are the bandwidths of these two? Because we were taught like this, this bandwidth is B, gain bandwidth product we are taught. So what do you think? So gain is 10 means, okay, 100 kilohertz, but gain is 1. It is not so. You see, what do you have to analyze it using the model I have given you, and you will find that the bandwidth of the first one is B by 2. Astonishing, but it is true. So that means, buffer is having bandwidth of B, but this inverting amplifier is having a gain this of B by 2. So that means, when you try to simply think, why don't I use inverting amplifier? Because gain is 1. Bandwidth is not 1 megahertz, bandwidth is 500 kilohertz. Okay. Similarly, you just see, I was mentioning, this differentiator. If you see, you have to analyze again using that model. You will find it is a beautiful band pass filter. If when you observe, this V0, second order band pass filter, and very this Q, you see, Q is dependent on the bandwidth of the op-amp, and CR values we have given. Okay, and pole frequency is dependent on this bandwidth and CR. This, a lot of people have worked on this, because actually now it has started again. Especially, some of the GSM and these mobiles, they said, I want to use minimum components for a filter. So this they started, active GMRC. Simply, just see this R1, R2, C and one op-amp. Why? You see, for a filter you need two energy storing elements. One is outside, C1. Other one is where? It is inside the op-amp. That is what, that means we call it as dominant pole. So the dominant pole is the one which I have modeled as B by S, that nothing but integrator. Minus B by S is nothing but integrate transfer function. So that means there is one internal this capacitor, integrator. That integrator and external capacitor together are realizing this. Actually, this was published by our Radhakrishna Rao of Texas Instruments, with IIT Madras. This in the 70s we have worked on this, and recently this one DMCO et al. These are all from Europe. They have fabricated the chips, and they never knew that all these things are very old. So I have written comments to this Journal of Solid State Circuits telling these are all very Purana circuits. Okay, now in those days, they used to ridicule, telling don't use circuits which depend on bandwidth of the op-amp, because bandwidth is dependent on temperature and power supply voltage. But today, people are using. That is because you can use some technique to compensate that effect. That actually was found by our Madras IIT only. One that is Dr. K. R. Radhakrishna Rao and one Srinivasan. That is known as follow the master filter. Okay, they only started this technique of automatic tuning of these filters, to the desired values by having on chip some feedback loop. Okay, so this people keep on rediscovering these things, in because of course necessity is there today, because power, I want to reduce number of op amps, I want to reduce area. That is okay, but you should at least acknowledge what has been done before. Now another famous circuit known as KHN, that is Kerwin, Huelsman and Newcomb Biquad, very famous one. This uses 3 op amps and it gives 3 transfer functions. That is, one low pass, high pass and this band pass. All the 3 in one. Okay, and very famous circuit. But there was one small limitation. That limitation was, you see, one of these today, what they say, there should not be any node where parasitic capacitance can exist in VLSI design. So for example, see here, virtual ground is no problem, because there is a parasitic, anything is there, there is no current that is drawn. Of course, that is old concept, because I have told you previous circuit, it is using virtual ground only. Okay. Now this virtual ground is no problem. Second, first, this middle op amp also no problem. But here you see this non-emitting input, suppose there is a parasitic capacitance to ground because of wiring or whatever it is, that will affect the transfer function. So this circuit was later replaced in 1975 itself by something known as, this is a very famous circuit, Tau Thomas Biquad. So you can see all op amps are having non-inverting input grounded. But what is the price you pay? Only 2 transfer functions are there. Because middle one is inverter, band pass, inverted band pass, low pass is there. So any other transfer function, if you want, we have to use one more op amp and 3 resistors. This is one of the most famous circuits, and all subsequent technologies like GMCR, OTAC, whatever it is today, they have to follow this. That's all. Because it is having some beautiful ideas. Like I am getting 2 transfer functions inside, one I can get outside, and all these capacitors are very safe, because you see one is connected to output of op amp, another is connected to virtual ground, so there is no problem of parasitics. Another beauty is the Q is controlled by just one resistance. That is, this R dash and QR dash. So Q independently I can control by using one resistor. Frequency I can independently control by varying these 2 capacitors. Gain you can control using this front end resistor R dash. This is what is known as orthogonal tuning. Orthogonal tuning means, if I change one parameter for achieving some spec, another parameter, if I change for another spec, they should not again ask me to go on redoing all these things. So that means independent control of parameters should be there. So this is the first circuit which has achieved that. That's why people blindly follow that. Okay. So if you say I want Q of 10, you simply say 10 times R dash you put there. You want gain of something, you select that input resistance properly. So that is how the beauty of this design. And today people want programmable resistors. Because so in fact some companies like Max, they have made MF10 some circuit design is there, some chip is there. So what they do is they have actually, suppose you want a resistor. A resistor I connect in parallel, then I can put transistors in series. Then I can use those bits to control. That means if I connect these two in parallel, resistance value will be 5K shunted by 2.5K. If I switch all 10K, 5K, but unfortunately what happens is this is not a good resistor. The reason is this is non-linear. Because when you say resistor, when you say 3-bit control, we expect uniform, that is all 0 to 7, values if I give 0 to 7. You should linearly should increase. Unfortunately, it doesn't increase linearly. You can calculate and see. That's why what people do is another way, they put resistors in series, then it is linear. That is, I have to put R, 2R like this, 4R, 8R like this I can put in series and select appropriate one. Then I can get any value from R to 255C if I want 8-bit control. But then, if both the cases, the pain here is the switch is not ideal. Because that MOS switch itself is having a resistance. If you see MOS transistor, maybe it have 1 kilo ohm can be there. So that means, this 2.5 kilo ohms and 1 kilo ohm are not just, 1 kilo ohm is not negligible. So that's why what happens, we have to select a, this properly, the technique for programming, so that your precision will be there. And today people also go for something like inductor, capacitor based. This is actually very old. In my childhood we used to read about M-derived filters, constant K filters and all that. That is using RLC filters. They call resistor, inductor, capacitor. Okay, but today inductor is a big headache to make. We can't fabricate in a VLSI chip, because we can only make very small values, like using annular inductor. That means I can create one resistor, like a spiral, one metal pattern like a spiral or hexagonal pattern, and I can create a small inductance of the order of maybe a few microhenries. Whereas the audio filters now you can't get. So that's why what thought. But very interesting property is there for this. They have very low sensitivity. Sensitivity means there is one beautiful theorem by one guy known as Orchard. No, not even a theorem, it is an argument. There is no proof for the argument, but everybody has to agree. He says these LC filters are the least sensitive. That means you change C3 a bit, 1%. Filter performance will not change much. You know why? He says there is something like coupling between the thing. It is not like like bike. I have told you Cascade design. First stage, suppose some trouble is there, it will pass on to the last stage. Second stage trouble will pass on to the last stage. Because there is no mutual interaction between the various. Whereas inductance, capacitance filters, the beauty is any small change anywhere will whole thing it will change in such a way that sensitivity is low. That there is a so that is Orchard's argument. So now what people thought is, why don't I mimic this then? Because the only component I don't have is inductance. So why don't I realize inductance somehow? So that's why two methods are there. I will not go through that. This is what one is known as frequency transformation. Again, telecom fellows wanted low pass filters. Okay, with this like this, what I have shown top one. So how to avoid that floating inductor? They simply one great person by the name Bruton. Bruton, what he told is, divide all components by S. Yes. So inductance SL becomes L, resistance. Resistance will become capacitance, because 1 by S means capacitance. 1 by SC will become 1 by S square C. That is known as, 1 by S square C is what? S is j omega. So minus 1 by omega square C. That is what is known as frequency dependent negative resistance. And they gave one beautiful circuit to realize this FDNR, that is frequency dependent negative resistance. So it is very simple now. So that means you can mimic this and get all the as a low sensitivity advantage of the LC filters to your active RC filter. So this is what is known as GIC, that is generalized impedance converter. So there are 5 components of 2 op-amps, So this can realize beautifully so-called frequency dependent native resistance by this choosing these appropriate values. Z1, Z3, Z5 capacitors, Z2, Z4 resistors. Then it realizes a frequency dependent negative resistance. So this you have to simply substitute in that each in the place of each of them. Circuit is having 4 op-amps, but it is a very good circuit. That means whatever was earlier difficult, in technology, you have realized very easily. Okay, similarly, there is one more method which people use frequently, known as operational simulation. Operational simulation, what to do? I don't want the earlier method is known as component simulation. That means I have replaced inductor with something else, capacitor with something else, resistor with something else. Here what I will do, I will mimic the equations at the nodes. For example, top circuit you see, I will write a equation at V1. I will write the Kirchhoff's current law at the node V0. I mimic that. You get the bottom circuit like this. This is one of the most famous circuits. This is known as leapfrog ladder. Leapfrog ladder, that name came because of some game which children play in UK, because that was invented by two guys, Girling and Good. You know why? It is like our Indian Coco. Coco, you see, one fellow will sit with his back, one side, other fellows will sit in the other side. So this in Britain, UK, it is called leapfrog. So very easily you can draw the circuit from the prototype. Top one is called prototype. You can write the bottom circuit, and values also you can just copy the values. So this is how evolution took place, and invariably people use. Now I will come to some of the latest ideas. See here, we are telling earlier virtual ground. Why they teach you? You see, op-amp gain is infinite. So this what Vg is minus V0 by A. A is 100,000, so it is 0. But if you use mass op-amp, this is not so. This only gain is 1000. So it is to say, suppose your output voltage is 1 volt, you can't just say ignore. 1 millivolt is coming there. Your signal itself, suppose I am giving 0.5 millivolts or 1 millivolt, it is comparable with the signal level. No? So that's why what happens, you should analyze the effect of that. This already we have seen. This is another, again, some interesting properties they have observed. See, this realizes a notch filter at VA. You know how? See, we should imagine, how do you get notch filter? Is one capacitor is there. Suppose I put an inductor across. At that resonant frequency, this is having infinite impedance. So it is it passes output 0. That means there is an inductor between Vi and Va terminal. That is op-amp with feedback resistor is nothing but a lossy inductor. So these all ideas were discovered as early as 1978. Okay, and people have built circuits using that. Now this is a very interesting one. Again, a lot of people are now working on this. They have built chips actually. Now how to get rid of the op-amp bandwidth problem? So one ingenious idea by one fellow by name Boutin in sometime in 80s. What he told is put a negative resistance which is parallel combination of R1 and R2. See how simple it is. So what he says is Vi by R1 plus V0 by R2 is Va into this one. So now suppose 1 by R1 is equal to 1 by R1 plus R2 negative, then this term is 0. That means this I am getting ideal op-amp now. So that means you have to realize the negative resistance of value parallel combination of whatever is connected between R1 and whatever is connected between input and this non-inverting input, inverting input and output and inverting input. Okay. So this is the idea, and this is actually theoretical idea given by that Boutin. So afterwards, actually I have actually analyzed. That means I was telling you, this negative resistance I have put there, and then it becomes, unfortunately, this op amp is also having its own bandwidth, finite bandwidth. So because of that, what happens is it will realize some approximate amplifier. That means it will not be an exact amplifier, but approximate. Now in 2019, this Zhang et al. And many other fellows have extended this. What they have done is they simply borrowed this idea without citing. And what they have told is this integrator I want to compensate. Again, for write one equation for Vg, then unfortunately what happens is unless you put a negative capacitance also minus C int across, it will not really this make this Vg 0, but that they have missed. That is simply, that means what they partially they could compensate. That's why they gave a big name for this, negative or assisted integrator. Those days we were not intelligent, so we didn't use such words. But now people use such words, negative or assisted integrator. Then I have written one this comment on this, comment article has come in Electrons Letters, telling that this is silly and they have to use one negative capacitance across this arm. Okay. So, but anyway, this they have, the only difference here is in olden days we never fabricated. Today they are fabricating. That is the only difference. Otherwise, ideas we were also having. This is how implementation is done. Now, how do you realize that negative resistance is? He says that cross GM you take, okay, because GM differential output if you have, you can get this current, which is positive or negative as you like by taking output from either inverting current output or non-inverting current. So this is how this has been designed, in actual circuit. That is implementation they have done. Now negative capacitance, if you want same technique, that is you have got a capacitance, give amplifier of gain 2, so Vi minus 2Vi will realize a minus C, that is all. So idea is same. So this also we have published. Now next we come to another important thing. The dynamic range depends on this noise actually, because op amp, we are MOS op amp especially is having very high YF by F, 1 by F noise. That means low frequency noise is more. So if you want to build audio filters and all, the noise, this effect is much worse. That is, noise is more compared to designing high frequency filter. So this has to be analyzed. Now how do you have to model the noise? So how do you model noise is by means of one noise voltage source and two noise current sources. Why two are required is noise current sources effect is dependent on the circuit resistance. That is, whatever you connect to the input, this inverting input left side, non-inverting input left side, and feedback between this inverting input and output. So that means resistances decide the this contribution of IN1, IN2. Whereas ENI doesn't bother about this external circuit. It is intrinsic noise voltage of the op amp. So these two are required to model. So that means, whenever you want to analyze the circuit, you have to substitute this model in place of your op amp. Then you can analyze. Of course, spice, this command, if you give dot noise, it will give. But you should know also what spice is doing. Spice is doing all this. Then, this offset, especially most op amps, have got large offset compared to bipolar op amps. In bipolar op amps, it will be there because there will be something like bias current which flows. For example, this circuit on the left, you see, so simply, what we'll do, we only write this bottom resistor we ignore. We don't write because we assume that it is used. Because, some chap may have some problem because of offset. Suppose, your gain is 100. Your offset voltage of the op amp is amplified 100 times. In MOS especially it is worse. So that's why what do this. But good design practice is to put it whether somebody needs or not. That is good design practice you should follow. So you should put parallel combination of R1 and R2 at the non-inverting input. This is the model we use for this left one, is the model used for offset voltage. Now, of course, a lot of tricks are there how to compensate the offset voltage. For example, in all these switch capacitors and all, we compensate. What we do is simple. We measure and subtract next time. I will just not. Then what afterwards, this what happened was people were thinking why to treat op-amp bandwidth as a headache. Why can't we use it? Because op-amp is nothing but integrator. So they put two integrators, in a feedback loop and realized filter. This is known as this active R filter. That means no capacitor will be there. The advantage is this performance is dependent on ratio of resistors. But frequency is dependent on bandwidth of the op-amp. That means, at least one problem you have solved. This is how actually it led to the concept that circuit should be designed with ratioed components. That means they should not depend on absolute value of component. They should depend on the ratio. This is how that next generation, I will just skip this. Switch capacitor filters have come. Before that, this now people are telling, why don't we use OTA? The reason is I was telling you, when you don't want to drive a resistive load, I can have a simple amplifier, this amplifier output stage can drive a high impedance load. Why can't I have current output itself? So this is how this OTA, of course, is a wrong word. OTA and GM people are using that is interchangeable way. But actually, GM is ideally it is a current source. Whereas OTA, is nothing but amplifier, op-amp with no driving stage. That means it can drive light capacitive load. So, but design is so simple using all this OTS, very analysis is very easy. This output current is V1 minus V2 GM1, and this second one, whatever I have shown you, that blue one is nothing but a resistor. So that means using a OTA, I can realize the resistor. The beauty is the gain is dependent only on the ratio of these GMs. Very nice control. This occupies very less area compared to having a conventional amplifier with this big resistance. You take this, how simple that is the current. Current passes through capacitor of impedance 1 by SC, you develop the output voltage. Okay. So the beauty is, whereas if you wanted this in conventional old technologies, op-amp, you need matching up these components. Then only you get a differential integrator. Whereas here I got a differential integrator just like that. Because the beauty of the OTA, that GM, will take input difference, converts to current and passes through the load voltage. Now filter, if you want this this amplifier, you load this resistor across with a capacitor, it becomes again an integrator. Now, this is what I was telling, tuning technique, So what they do is, this popularized by Savidishwan Banu, but they have actually taken, they have quoted, of course, this Radhakrishna Rao's idea, that is follow the master filter. So what we have got? We have got an oscillator, which uses same technology. That means same resistors it is using. Same resistors. Now your circuit is using also resistors, but dimensions and all are similar. That means they are ratioed. So what happens is, now I will bring the voltage, control voltage, of these resistors we see in my this oscillator, by locking it using a phase lock loop. That means I have got an external clock. I will lock this oscillator frequency to that. Till it locks, I keep on controlling this control voltage of the resistors, gate voltage of the resistor. So once I get it, that voltage I apply to my circuit, my filter, which is having similar ratio components. So that means, automatically all the resistors in my filter also are brought to the desired value. So this is one of the most beautiful techniques. But the point here is, if you want to use continuous time filters like CT and OTSA filters, you need invariably, this is the overhead for you. That means you should have an oscillator, some method or mechanism should be there to have comparison with some reference, then controlling this to bring it to the original value. Now this is next generation switch capacitor filters have come. So here you can see this is based on ingenious idea, that you can use two switches, one capacitor to realize the resistance. Very simple idea. So you just take, suppose I charge the capacitor to V1 and in phase 2 I discharge to V2. What is charge that has flown is C times V1 minus CV2, because the charge has to flow somewhere. It has acquired originally CV1 and finally it is having CV2. That means the charge has flown. Okay. Now this charge has flown in a time interval of t. That means the time take phi1 plus phi2 is your time interval. So this is nothing but C into V1 minus V2 by t, or equivalently I have got one time constant, that is resistance value, which is T by C, because current is V1 minus V2 by R. So R is T by C. So beauty here is this resistance value is dependent only on the sampling frequency, that is T sampling period, and this capacitance value. So frequency translation I can do. Suppose if you have designed a filter for 1 kilohertz, I want to change it for 2 kilohertz, I will say please change the sampling frequency double. So I can double or decrease sampling frequency and change my request. Similar, next another point is, suppose you want now time constant, that is RC. What is RC? R1, C2. One R1 is T by C1. So T by C1 into C2. C2 by C1 controls the time constant. That means ratio controls exactly the required frequency, because sampling frequency and ratio only decide. So this is one of the fundamental contributions of Robert W. Broderson and his students, okay, which has revolutionized this filter design concepts in those days. And then of course a lot of new idea, then what they thought was this circuit nobody uses actually. Why? This C actually is plagued by the parasitic capacitance. So that means your actual time constant resistance realized is T by C plus Cp. So this is a pain. So that's why what the beautiful ingenious technique they have invented was something known as stray insensitive. Stray insensitive means let this C1 have parasitic on the left or right. I don't care, because I trade off with switches. I need, earlier I have 2 switches, now I have put 4 switches. So what I will do, you see, you can see left node is charged to V1, discharged to ground. So that charge doesn't enter the circuit. Similarly here also it is switched between ground and virtual ground, so no problem. So that means this is what is known as strain sensitive inverting integrator. And next beauty is, by just interchanging the first 2 switches, I can get inversion by the in a passive way. That means the switches themselves, I charge it to something, then I say you change your terminals. That means whatever this V1 positive it has acquired, it becomes negative. Positive will be here. So that means it is able to invert also. So that means whatever I have shown you, tau times biquad, this that in between, this one amplifier was there. That amplifier is not required, because I am able to show you 2 circuits now. One non-inverting integrator, one inverting integrator. Connect them in feedback loop, it becomes a filter. That is one of the most famous circuit known as Fleischer-Lacker biquad. You see here, if I want loss, I have to use one resistance. Now, what is the difference between capacitor and resistor? Resistor has no memory, so I am destroying the memory in one phase. I am connecting it only in this one phase. Other phase I will say, forget about what you have learned. Similarly, input side we have seen already. So this is how the switch capacitor technology, this is a full second order, that is biquad. Anything it will generate. One of the most outstanding circuits, this has come from AT&T Bell Laboratories. Then similarly switch, very easy to show switch, but actually what is a switch now? Switch is nothing but this 2 switches in parallel. The reason is switch is having its own problem. There is something known as clock feed through. Because there is a capacitance between this gate and source, gate and drain. Gate and drain, this capacitance will make a spike to come whenever that this phi 1 I am inverting phi 1 let us say phi 1 bar. Whenever edge it comes to that edge, every edge there is a spike at this D terminal. Similarly, there is a spike for the second one. But what happens now? Because I am driving them using equal and opposite clocks, positive spike and negative spike will cancel at D. But price you pay is this you need, that means switch is not simply one switch, it is two switches, and even size of the switches is chosen such a way, okay, because PMOS transistor and NMOS transistor are different. So what they do, they design in such a way that this spikes will exactly cancel. Okay, this is how this is done. This I will skip. So these are amplifiers. Now you can see books, like Holland and Alvin. This is what I told you. The resistor, if you want programmable, you even here the trouble comes. Whenever you short, it is not real short, because it is nothing but volt that actual resistor paralleled by the switch resistance. So you should take into account all these and then do. And today people use invariably sigma delta converters. I told you, because analog portion is very simple. Only I need two op-amp based integrator, two switch capacitor integrators, and that integrator will itself take care of these differencing blocks. And one comparator I need, and one D flip flop. That is simplest circuit. This is a programmable capacitor. Capacitor you can connect in parallel, C2, C4, C8, C, like this, So you can get digital. Whereas resistors you can't connect in parallel, you can connect in series only. So this, a programmable capacitor array they call PCA. So PCA invariably we use whenever we need programmability. Then, all these things finally they have something on a figure of merit. That is, finally there should be one figure of merit to compare X design is better than Y design or not. So power dissipation, that is whatever is proportional, that is power dissipation is more, figure of merit is more. Power dissipation is less. So whatever is proportional you put in the this numerator, that is more it will be. Whatever is these other things, they have put in the denominator. So this is one of the universal figures of merit. Of course, figures of merit, different fellows define different things. There is one proverb, beauty lies in the beholder's eyes. Okay, so I can say some circuit is good or some circuit is bad based on suitable figure of merit. Now, latest one is ring oscillator based filter. Here the important observation is, here this what it says, phase is integral of frequency, frequency derivative of phase. So what they are telling is analog integrator is analogy is used in this. So they use a VCO and they detect the phase, and that is converted to voltage. Okay, and the VCO can be used based on ring oscillator, that is number of odd inverters with inverter delay. And you can do current mode also, that is current control oscillator also you can have. Okay. A lot of work is going on now today on, for example, what they do, they take the circuits like Tau Thomas Biquad. Then they substitute that integrator portion, you can see, by VCO, and then this charge pump and this phase detector, these are things you have to do. So that means, you can just replace integrators by this. This is the latest one. I don't take much. Similarly, next one is inverter based filters. See, as I told you, why should I use a complicated op-amp? So of course, this idea also is very old, but now it has become more popular, because simply CMOS inverter I use. Instead of this is a very recent one, some big sigma delta modulator, he wanted a cascade of integrators filter, third order filter. Simply, he says use this simple CMOS inverter. So this is how, you can realize, this differential input you give, differential output I get. So I can reduce this area. But then, of course, they should have one common mode feedback loop. That's why, this extra circuit is there, which works in parallel to find out what is the this output difference between V0 minus V0 plus, then it gives a control voltage to control this, so that this balancing is achieved. So the conclusion is variety of options are available, and new design techniques focus on one of the or more, like reduction of area, power consumption, and extending the frequency range of operation. And then people are more now focusing on transistor level design instead of building block based approach, because olden days you would say use op-amps, OTS and all, but now because I may be constrained. If I say use a op-amp, you imagine our CMOS op-amp is having inside some 7 or 8 transistors. All those transistors I need. Instead of that, why don't I have a fresh look and try to use latest version? That's all. If you have any questions, I will be able to. Yes.
Hello.
Yes.
Yeah. Just a minute. Yeah. We have come to the end of the presentation. Thank you very much, sir.
Welcome.
For your insightful presentation. I will request everyone to, if possible, can you turn on your video so that I can capture the presence. Thank you once again. Thanks for spending the evening today with us.
Yes.
And I will thank everyone who was in the bridge, and we'll hope to see you again. And we keep organizing this kind of webinars at least once in a month. So hope for the next one, and it will be early in the July.
Okay.
Thank you very much.
Welcome.